I am not a functional programmer. I am a structural proof theorist, but my students are functional programmers, and I would like to teach them logic. So before we heard about teaching in primary schools, and we heard about teaching in what I presume was undergraduate introductory functional programming courses. Now we are at a graduate course in logic. And basically, our observations are that pen and paper proofs are good and nice, but the connections to the real world are not always very clear. And another thing is that textbooks are often wrong. And if they're not wrong, at least they sweep complexities under the rug, so they never really say how you're supposed to do it. They just say, well, you can do it somehow. So what we've done is used functional programming to sort of get out of some of these issues. And we're doing functional programming in a proof assistant called Isabelle Hall. So I will show a few programs. It will be very brief, and they might not look exactly like what you're used to. So our approach is to define every concept in our course as a functional program, and then we will use this proof assistant, which you can think of as just a functional programming language that has a very strong type system, though this is not quite the case for Isabelle, to prove any theorems we have. And this means that, of course, we still have a textbook, so the students can read all the informal definitions and proofs, but they can also consult the formalization if they need more details or if they don't believe us. Also, since we have implementations, they can actually do experiments, they can run the programs, and they can change the programs. And because we have a proof assistant, you cannot sort of, you can change the program, and if the proof is still correct, it will still say, yes, that's fine. But if changing the program breaks the proof, then the proof assistant will tell them that. And finally, Isabelle Hall allows us to export to languages such as Haskell and Scala, also SML, and very recently F#, but that's still very experimental. So our contributions basically are functional implementations of a lot of logical systems, formally verified proof of properties of these systems, and then finally an evaluation of the usefulness of our approach. So I'll start out giving a real basic, I mean, we spent 13 weeks of on this, so this will be very brief, and read the paper. There'll be a link at the end if you want to actually understand all of it. And then at the end, I will talk about what our students think about this. So here's some logic. We have some syntax and some semantics. So this is the easiest thing I could think of. We have propositions. They are either true or false. Then we have falsity. It is a proposition that is just always false. And we have implication. So implication means if the proposition P is true, then Q also has to be true, and then the entire thing is true. Basically what I just said is the semantics. So we have an interpretation that says which things are true and which things are false. And to find out if a proposition is true, we just look in the interpretation whether it's true or not. Falsity is just always false, and implication, if P is true, then Q also has to be true. Okay, so what do we want to find out? Now we have some logic, and really we have formulas that we want to know some things about. And one of the things we want to know is satisfiability. So if we have a formula, can we pick a combination of true and false for the propositions that makes it true? And validity, basically no matter what we pick, is it still true? And of course we can just try all possible options. This is a very easy but very stupid way to do it because it scales exponentially. So instead we will use what's called a sequent calculus. This is one of several possible systems. And basically this is a set of rules. So there is this, this is called a turnstile. It's like the ones you go through in the trains. And we have some assumptions to the left and some goals to the right. And the assumptions and goals are formulas of any kind. So our basic rule is that if we assume something, then we have that thing as a goal, then we're done. Then we don't really need to prove anything. We're just immediately finished. If we have falsity as an assumption, we're also done because then something went wrong, basically. Or if we assume something false, then we can just conclude whatever we want. This doesn't really work. Okay, but anyway, we have the implication left rule, which says that if we have an implication as an assumption, then if we can prove P, then we can assume Q. And this sort of splits it into two branches because there's one way we do one thing and one way we do the other. And then if we want to prove an implication, then we can assume the left thing and prove the right thing. Okay, so now we have a logic and we have a way to prove things about the logic. So really what we want now is for the proofs to actually have something to do with whether things are true or false or not. So we have something called soundness, which means that if our system is sound, then if we can construct a proof using the rules, then the formula actually is valid. And completeness is the other way around, that if the formula is valid, we can somehow prove it using the system. And of course, in a textbook, this is very easy to prove. We just say, well, that's by induction. And what we're doing induction on is these rules. They form a tree, so by induction on the tree, we're done. And I hope everyone immediately sees why that is true. So of course, it's not actually that easy, because it's not really clear why this terminates at all. I mean, you can just use the proofs in any order, essentially, right, or the rules. So it's not really clear that we will always get to either this one or this one. Okay, so now let's get into the functional programming to make a computer actually check that this does hold. So we have a data type. It's the same data type as I just explained, sort of in an informal way. So again, we have propositions. They have some sort of name. We don't care what the type is. We have falsity, and we have implications. Then we have the semantics, which takes some map I and then just looks up n, the name, in I. This is just always false. And then here starts the Isabelle things, where we can just write implication directly. So this is not sort of a mathified syntax. This is the actual syntax of Isabelle. And also we can just say for all p in some set, so Isabelle supports sets natively, and these are real mathematical sets. So our sequent calculus, basically we're saying if all the assumptions are true, then there must be one of the goals that is also true, and if this is the case, then the sequent calculus sort of should say, yes, there is a proof, right? Okay, so then we need some basic functions. We have a member function. There's nothing shady about it. Oh, this would be nice if this worked, though. It's just a member function, and let's prove that. So we say if member called on M and A returns true, then M is in the set A, and this is by induction on A. So this is a proof in Isabelle, and then we use the simplifier, which is some automation that just does rewriting, basically. We also have a common function. It checks whether two lists have an element in common. So if it's a member, then it's in common. If it's a member in the other one, and otherwise we just check the rest of the lists. And again, we can see that this is actually the case by induction on B this time. So these are some very basic proofs and definitions. Here's a little bit of a more complicated definition. This function simulates applying the rules. I will not go into how it works, because that will take an hour. That's how long it normally takes in the lecture anyway. So I'm not going to go too much into that. But basically we're saying, first of all, we actually hit all the patterns. This is by pattern completeness. So we will not find any formula that we cannot call this function on. And then we have to prove termination, because Isabelle requires all functions to terminate. So we prove termination by some measure. And the thing we're measuring is the sum. So again, Isabelle has some crazy syntax here, so we just write the sum symbol of the sizes of all the formulas in the assumptions or the goals. So C and D here are the assumptions and goals. And eventually that will become 0 as we look at each of the formulas. I do not expect, look in the paper if you want to really understand this, because we have some more explanations there. Okay, and then our main theorem, which covers both soundness and completeness, is that if it is the case that for all interpretations there actually is, it actually is a valid formula. So these are again the assumptions and the goals. Then this formula or this function will terminate, and it will return true. And here we do it by induction. So as I said before, the proof is obvious. It's by induction. And we use the induction following this sort of setup, so these cases. And then here's some more automation that does it. So basically we have the same as the textbook proof that just says by induction, except this time we actually have a proof assistant, a computer that tells us that it actually is just by induction. So there's no hidden stuff, except that we actually had to think about, okay, why does this induction actually, like, what is the base case? And the base case here is that actually eventually there will be no more formulas left to look at. Okay, and so finally we can say, what if we don't have any assumptions? We just want to prove some formula. Then we just put in the formula, let everything else be empty, so no assumptions. And then we get exactly that the prover returns true if and only if for all interpretations, so assignments of true and false to values or to propositions, the formula is true in all those interpretations. And this is just a simple consequence of the previous theorem. So this was just a really, really quick overview. Of course, getting to this takes a few weeks normally in our course. So the course is a master level course. We expect our students to already be pretty proficient functional programmers. Unfortunately, many of them are not, but and most of them have never seen formal logic before. So we spend a lot of time on this. And we have some lectures, we have some exercise sessions with TAs. So this is a physical course now. Last year it was not. And we have some assignments where they basically have to prove things and define functions in Isabelle. The exam is also all programming and proving things in Isabelle. So an exam question could be define a function that doubles the elements in a list and prove that it actually does that in a completely formal way. And of course, we also have some more logical-oriented questions. So we had 43 students after the first few weeks. So we have a bit of a weird people drop out, and it's not an issue because they can audit courses for the first few weeks. And here's the curriculum. I will not go through it way too much, but what we just covered in 5 minutes is the first 2 weeks. Then we have first order logic, which is the same as we just covered, except you can add in quantifiers, so for all or exists. Then we have natural deduction, it's an alternative proof system, and the LCF approach, which is how to design theorem provers. Then ISAR is the proof language of Isabelle. We have intuitionistic logic, which is where you can't do proofs by contradiction, and foundations of math. Then we do proof by contradiction, classical logic, higher order logic, and type theory. And by type theory here, we mean logic, not the kind of type theory for programming languages. Then proofs in sequent calculus in more details, and finally some metatheory and algorithms for actually writing automation in Isabelle. And finally a little bit of program verification. Now this brings us to the next part, which is what did our students think about this? So we asked them. So we had an anonymous survey, and about half answered. And we had 6 hypotheses that we kind of wanted to confirm or deny. And this, we thought we needed 12 questions for this. So here they are. I will not go through them all now, but I'll go through them one by one and then read them out as we sort of see them. So first of all, we thought that concrete implementations in a programming language actually aids understanding of concepts and logic. So this is kind of the basic thing. And so to find out, we asked basically, did Isabelle help you? Did you think it was useful? Did the course material, the reading material, was that useful? And were the lectures useful? Not so much. And how much do you think it's important to sort of be able to experiment with your own examples? And from this, we see that actually they thought the Isabelle things were very essential to actually learning anything. Of course, we didn't actually have their grades. This is very new, so they hadn't done the exam yet. And also, we had a whole GDPR thing, so I don't actually know, so we'll call this plausible. Next, that students actually experiment with definitions to gain understanding. And we have, most did it often, and then some people did it almost never, and I'll come back to some theories about this. Then we thought that our formalizations make it clear to students how to implement the concepts in practice, and we can conclude that it's not really. I must say, generally, this is not really unexpected, because this is quite difficult. I mean, formal proofs are generally known to be very expensive and less used in industry just because it's hard to justify spending so much time on it, because it is quite difficult. But I'll come back to what we think we might be able to do next year to improve on this. Then also that they're able to design and implement their own logical systems. And again, we must say, slightly confident at best is what the students thought about this. Not all goals were met. We're still evolving. So now the final one was that actually functional programming was useful for our course, and there is a statistically significant but small to moderate association here. Read the paper for the exact numbers and also how we calculated that. And similarly, so this is all of our students that did not really know anything about functional programming before starting the course, even though it was a prerequisite. But we see that this has been reduced quite significantly after the course. So at least they got that out of it, if nothing else. And this is a large positive, statistically significant effect. Again, read the paper for the numbers. Okay, so after having done the survey, we noticed some interesting trends. None of this is statistically significant or valid in any way. This is post-hoc analysis, so do not take anything I say from now on as true. But it seems that students who think experimentation is more important actually do it less in Isabelle, which is sort of counterintuitive. We think it might be because they just do it on paper, because they're used to doing that. Students who were not confident functional programmers at the end were also less confident that they could actually implement something, which makes sense, but we don't have evidence to prove it, or it seems reasonable. Also, students do not seem to get elevated past sort of a basic understanding of functional programming. So the people who already were quite confident functional programmers did not get better. And finally, advanced concepts in functional programming does not really seem to be needed at all for the course. And this is actually by design. So you see I wrote out the member function instead of just saying it's the member function. And we try to really not have too many folds and functors and stuff like that to not confuse people unnecessarily. Because again, remember, this is a logic course, this is not a functional programming course. Okay, so there are some open questions for future work. So one of them is about why do students who think experimentation is important seem to do it less? Probably because they do it on paper is my best guess, also from like seeing them do it. Then does functional programming experience play a significant role in knowing how to implement concepts in practice? Because it might also just be that students don't know how to implement anything in practice. We don't know, we don't have the statistics to say. Does it play a significant role in understanding how to design and implement their own systems? Again, maybe they just don't know how to design anything. And does it actually have a positive effect on functional programming skill for people who are already functional programmers? We think not, but we don't have statistics to conclusively say yet. So some ideas. They didn't like the lectures, so we should reduce them, maybe, or just make them better, I guess. But it seems like they really need to get their hands in from sort of my personal experience. To sort of make them feel more confident in actually implementing stuff, maybe we should add a project-based assignment. This may mean that we need to make our course bigger, or like, you know, more ECTS points. So this may not be possible, but it's an option. Maybe we can find some time by not having lectures. And we should just generally consider how to teach students how to actually design their own systems and use this in practice. Of course, for future surveys, we could have larger sample sizes. We could pursue some of the open questions I mentioned. We could add information on grades in other courses, so to sort of know if they are really good functional programmers or not. But this would require a whole GDPR thing and also the involvement of the ethics committee and our institute and stuff like that. We can try to reduce self-selection bias. This is generally difficult. And we would like to compare our course to pen and paper courses, but we don't really know how because it's very different. And so it seems to be difficult to find measures that would work for both. So in conclusion, I think our approach seems promising, but it definitely needs more work, especially to be actually, to have sort of a pipeline into some industrial use. So hopefully, as Kevin and Lucas said, it would be nice for us also to have some industrial partners come in if they work with logic to sort of make students see what is this used for and how do people actually do it. Students generally find it hard to implement their own designs and to design their own things. So this is also kind of an issue. And I'd just like to say that there are lots of opportunities for further research, and especially for graduate courses, there is actually not really a lot of research on this sort of thing. So this is very preliminary, of course, but it would be great for anyone else who is thinking about this to sort of pursue this. So just at the end, some propaganda. So for more information on Isabelle, you can go to isabelle.systems. It has a lot of links to various things, including some books and tutorials if you'd like to learn about it or come talk to me. This is our paper. This is like the part that you need to Google if you don't want this link, which has all the actual numbers and why those statistical methods are appropriate. And also it has all the code I showed you, but with some explanations. That's more than like 2 minutes. And finally, you can go to my website where we have some other related papers, because we also have an undergraduate course and we have some considerations on how to design exams and assignments that sort of use proof assistance in a reasonable way. Okay, so that's it for me. So thank you.
Okay, questions for Frederik, and also please mark the evaluation of the talk.
I will be collecting votes on.
So I understand that the material that you described covers usually 1 year, first year course in set theory and logic.
Yes.
So the question is, why did you decide to shorten it so dramatically?
Well, first of all, this is a graduate course, so we expect them to do more, basically. Also, we just don't have the time, to be honest. So we have to sort of speed it up a bit. But we do feel, or we do experience that having these implementations makes it much easier for students to see, for example, the parallels between natural deduction and sequent calculus, because when they compare the programs, it's basically the same program. So I think this also means that we can go a little bit faster than usual. But yes, of course, it is a quite compressed curriculum. And there are some things we just straight up skip. We do not talk about the compactness theorem, for example, also because we do not feel that it has real-world use cases, essentially. But yes, I mean, it's a quite compressed course. So as we see, there are some other questions, so we can talk after.
Hi. So you mentioned that it is very expensive to write proofs for that can be formally verified. So do you think, and probably it's like the main reason that it's not adopted mainstream by industry, and it's probably not likely to be happening in like next few years. Do you think, or maybe do you know about any research or any solutions that can help in automatic proving of theorems, maybe using artificial intelligence or stuff like that?
Yes, actually my research is not on this, it's on exactly what you described. And my approach is basically to limit the languages, so just make DSLs that are simpler, you can express less things, but then also the proofs become automatic. So basically it's just a type checker. There is research on what you mentioned with artificial intelligence. I'll be happy to, I don't remember the references, but I'll be happy to find them for you. This is something that, you know this Copilot thing. Also, there is a similar thing for proof assistance. And many proofs look quite similar, so it's possible. There is also something called a hammer, a concept in automatic proof assistance, which basically is an SMT solver, or a lot of SMT solvers attached to a proof assistant that then can find many theorems for you, or so like semi-automatic assisted proof technologies. But yes, there's a lot of research on this.
Okay, thank you.
Okay, I think, okay, let's do one more quick question.
Thank you for the talk, and just a recommendation to get more data.
Yes.
Just give them 5 credits or 5% of the course if they do the questionnaire, and then bump every grade by 5%.
Yes, this does introduce some bias as well, but it might remove self-selection bias, but then it introduces compensation bias. So we'll see about that. But yeah, of course, this is always an issue, right? Is how do you actually make students do something that they don't get paid for in either credits or money? So yeah, we're trying to think about that. Basically, my approach now is to go and back them while they are doing the exercises. But yeah, are we out of time?
Okay, yeah, thank you very much.